Hey guys, welcome back. In this video, we're going to revisit the two first problems from Project Euler and talk about faster ways to do them. As I've gone through some of these problems and tried to refine and improve some of the methods, I realized some of the early problems we did kind of slow, and we can actually provide much in the case of the first two much faster ways of doing it. And we're going to show that with when I run these. We're going to look at the console, the time that it does in the console. So this is the way that we did it the first time around in my first video. We're going to talk about a new way. Now you can see right here, that's sort of given away what trick we're going to use for this. Gauss was a mathematician, and he's associated with this concept of summing a series of integers from 1 to x or 1 to n very quickly. If you'll notice that the series from 1 to 100, you can actually pair them off with 1 and 100, 99 and 2, 3 and 98, and so on and so on. And each of those pairs is going to equal 101 down until 50, and 51 still going to equal 100, 101. So that's 50 pairs of numbers that equal 101. And so we can say that the series of numbers from 1 to 100 are equal to 50 times 101. The mathematical way to represent that for any given set of 1 to n is n plus 1 divided by 2. In the case of 100, that's 100 times 101 divided by 2. And we can see this is going to be the 101 right here. We've got 2 and 100 right here. If we divide 100 by 2, we get 50. So this is basically right there. So now that's part of what we need to get to where we need to get for this. The problem is that we're not counting every single number. We're only counting every third and every fifth. So how do we solve that problem? Well, as it turns out, you can divide the series initially by the divisor that we're passing in right here. And then when you're done getting the Gauss sum, you can multiply it back in, and you can get around that issue. So that's what we're going to do right here is get around that. And you can sort of see this is the Gauss sum right here that I've just described right here. And so this new num, what we're doing is we're passing in this, supposing that the boundary that we're passing in is 100, we can see that when we pass it in, pass num, we're subtracting it by 1. We're dividing it by the multiplier. There's a particular reason that we're doing this, because what the problem is calling for is below the number that we're passing in, not the number itself. So when Euler says find the sum of multiples below 1,000, so if it didn't say below, if it said up to 1,000, we wouldn't be subtracting 1 from here. But because it is, we have to subtract 1. And then we divide it by the multiplier, and then we need to get the integer value. We need to round down for that. So we pass that in, then we get the Gauss sum, and then we take that multiplier and put it back in. So for example, if we're doing this with the number of digits from 1 to 100, and let's include 100 to make our math a little bit easier here, from 1 to 100 that are divisible by 5. If we tried to sum them all up, before we get to this part, we divide 100 by 5, we get 20. So we do 20 times 21 divided by 2, or 210. And if you count up 5, 10, 15, 20, 25, 30, so on, you will get 210. I'm not going to do it for you right here, but you can check the math on that and see that it in fact works. So we can do that for 3 and for 5. The problem is that there are numbers that we're counting twice because they are divisible by both 3 and 5. So what do we need to do? We need to subtract those numbers from this sum. So 15 is getting counted twice here. So how do we solve that? We subtract 15 from here. Easy. 30 is getting counted twice. 45 is getting counted twice. 60 is getting counted twice. 75 and 90 are all getting counted twice. So we need to subtract that, and we do that with this. So let's go ahead and take a look at running this. We can see 5. That's a lot faster than what we initially had, because here we're running a loop and we're checking each instance. Here we're not running a loop. We're just running, this is O of 1 time complexity. This is O of n time complexity. So if we increase this is 400 right now. The problem that we had was 1,000. We set that, we're going to see that the time is going to grow. This actually went down. If we try rerunning it, there's probably going to be an average uptick, but it's going to be small. So if we go to 1,000, we should notice an uptick in each of them. Still not an uptick in that one, but we're seeing an increase on the other one. Probably going to be running into some issues where we're no longer getting values that can be represented by integers. Again, this is running, basically the same speed. This is increasing over time though. So this one runs about 0.15 seconds. Its time complexity really doesn't increase with the larger numbers. Maybe the computations get slightly more difficult, but not really, at least for a computer, obviously. But the time complexity really takes a toll on it as time goes on, comparatively. Let's go ahead and take a look at the second one. That was the even Fibonacci number. So if you'll recall that prompt, what we were asked to do was each new term in the Fibonacci sequence is generated, by the normal means. 1, 1, 1, 1 plus 1 is 2, 1 and 2 is 3, etc. And we need to find the sum of the even valued terms in the Fibonacci sequence, which do not exceed 4 million. So how do we do that? Okay. It may not be obvious, but the sum of, or the Fibonacci series alternates odd, odd, even, odd, odd, even, odd, odd, even. And we can actually, provide, more or less a rough proof for this, and it's in the comments above. But if you look, 1, 1, 2, 3, 5, 8, 13, 21, what is that? That is 34. So an odd number plus an odd number are always going to be even. They have to be. It's always the case that is the case. An odd number plus an even number is always going to be odd. Well, you start out with 2 odd numbers, you're guaranteed an even number on the next round. If you start with an even number and an odd number, you're guaranteed an odd number. If you start with an odd number and an even number, you're guaranteed an odd number. Now you got 2 odd numbers, so you're going back to even, right? So the Fibonacci series has to be such that every third number is going to be even. With that in mind, before I was iterating by 2 because it made sense, right? You're taking the sum of the 2 previous terms. You can sort of intuitively think of the Fibonacci sequence as an iteration in sets of 2. But if we change that around and start thinking of it as iterating in steps of 3, we can actually come up with a better solution. And how do we do that? So the first thing that we're going to do is feed in the first three. We can set C to equal A and B here. Doesn't matter. It's either got to be 2 or A plus B. And then we do while C is less than the limit. We don't care what the value of A is or B, because we're never going to be adding them into the return value, because C is always going to be our even number. Because when we go through, we set A as the number that comes after C, B as the number that comes after that new A value, and then we set C as the number that comes after that B value. So A starts out odd, B starts out as odd, C must be even. A is the number to come after C, has to be odd. B comes after A, has to be odd. C now has to be even because the two previous numbers are odd. So we start out by adding the C to the sum. We get the new numbers for the next go around, and we add it again until finally we get the answer. And if you look here, you'll see again we've got a much faster solution. Now, I don't. It's not immediately obvious what exactly is going on here. There are less loops that are needed for this because we're grouping in sets of 3 instead of sets of 2. There's also no if checks, so that could be speeding it up. But regardless, we notice a marked improvement because this loop is checking is making 33% less go arounds on that. There's no if checks to make sure that it's even, because we know that this mathematically has to be even. There's no concerns about making sure anything's ever below the boundary limit. Yeah, so if we give it a few more test rounds, we can see, this is just significantly fast. I don't know how much bigger we could get this number. We can try feeding in an extra 0. I don't know if, yeah. See, this isn't even growing that much, but you can see again, the top one is growing much more rapidly. I think eventually we're going to run out of storage for a regular integer value, but for right now, it seems to be going. This actually took shorter this time, but still, this is going significantly faster. Yeah, so I hope this was at least a little bit of interest to you. I know it was a little bit of interest to me when I went back to revisit some of these problems to see if I could find better solutions. These were the two that stuck out to me. I think really the rest of them were just kind of minor improvements to the methods that I had already previously employed. As always, let me know in the comments what you think. Smash the like button, hit the subscribe button, and yeah, I'll see you guys next time.